Hello, everyone. Welcome back. Today I'm going to be talking about mutually exclusive events, and this is actually going to be our very last lesson in this unit about basic probability, introducing us to some of the basic concepts in probability. So, what are mutually exclusive events? Well, if A and B are two events that have no outcomes in common, then those events are said to be mutually exclusive. In other words, these two events cannot occur at the same time. So I'm going to give you an example. Let's say that event A was rolling a 3 on a die, and event B was rolling 6 on a die. Well, those two outcomes cannot occur at the same time, right? We could roll a 3 and then a 6, but is it possible to do both in the same roll? Well, no, it's not, right? This isn't possible, right? Or, for example, what are some examples of events that are not mutually exclusive, though, right? An example is being a dog owner and being a cat owner. It's possible for someone to own both a dog and a cat. So that would not be mutually exclusive because it's possible for the same person to own both, right? Or, for example, is it possible to roll an even number and to also roll a 6? Well, yes, that is possible because if we roll a 6, that's also an even number. However, it's not always going to be the case. They're not the exact same event because we also could roll a 2 or a 4, but they're still not mutually exclusive events because there is an outcome, which is rolling a 6, that satisfies both events of rolling a 6 and rolling an even number. However, if I was to say, you know, event A is rolling an odd number on a die, and event B is rolling a 6, well, those are mutually exclusive, right? Because if we've rolled a 6, then we have not rolled an odd number. And if we have rolled an odd number roll, then that number is not a 6, right? So no. So those would be mutually exclusive. So the two events to not be mutually exclusive, they don't have to be the same event, but they have to be two events that cannot possibly occur at the same time, in which there is no scenario where both of those events are true at once. So basically, if events A and B are mutually exclusive, then the probability of A or B occurring is the probability of A plus the probability of B. So the probability of one of those events occurring is going to be adding the two up. Now, this is only true about mutually exclusive events, and we'll talk about why this actually isn't true and where we have to add an extra layer to this for non-mutually exclusive events. We did touch on this a little bit before during when we talked about Venn diagrams, but I want to go into more detail in here today. So let's start with example 1, though. It says if someone rolled a die, what is the probability they rolled a 3 or a 4? So event A is rolled a 3. Event B is rolled a 4, right? So what's the probability of each of them? The probability that we rolled a 3 or a 4 is the probability we rolled a 3 plus the probability we rolled a 4, right? Now, what's the probability of rolling a 3 on a 6-sided die? Well, that's 1 in 6. What's the probability of rolling a 4 on a 6-sided die? 1 in 6. So therefore, 2 in 6, or 1/3, is going to be the final answer. The probability of rolling a 3 or a 4 is 1/3. You could also argue that that's the case because, we have those are two separate events, 2, and then the overall number of events is 6. So you could also just jump to it that way in this simple example. There are other examples, though, in the future where doing it this way, with the formula, may be more helpful, right? To kind of get things making more sense. Okay, so there's an example of mutually exclusive events and how we can just add up the probabilities to find out the probability that one or the other would happen, because we're not really double counting anything, because there's no chance that both of them could happen at the same time. They're two completely separate things where either one can happen or the other can happen or none of them can happen, but they can't both happen at the same time. Now let's talk about non-mutually exclusive events, and these are basically any events that are not mutually exclusive, so just the opposite of what we talked about. If two events A and B have no outcomes in common, then they are mutually exclusive. So, if two events A and B have some outcomes in common, those events are said to be non mutually exclusive. So, those two events can occur at the same time. Now, does that mean they're the exact same event and they always occur at the same time? Well, no, not necessarily. Typically, non mutually exclusive events are still different, but they have certain elements in common, right? Certain things can happen at the same time. So the formula for this is that A or B must be probability of A plus probability of B minus the intersection of A and B. So minus the probability that both A and B are the case. Now, why would that be? Well, that's because we're going to double count people if we don't do this step. Now, why would we double count people? Let me explain. So let's say, for example, that I have over here cat owners, and over here I have dog owners. And let's say that there are 5 people who own both a cat and a dog, 10 people who just own a cat, and 6 people that just own a dog. If I was to just add up probability A and B, right, the probability that a randomly selected person from this group of cat and dog owners owns a cat, I would say, well, that's going to be 15 over what's the total number? 10 plus 5 plus 6 is 21, right? So I added up the two numbers in the cat bubble, and I put it over 21, which is the total number of all people here. We have 10 plus 5 plus 6 people in all. And then I'm going to add B, which is going to be dog owners, which is going to be this 5 again, right? Because this 5 is also in dog owners plus 6, so 11 over 21, right? Now, if I add this up, we're going to actually get something greater than 1 here. Now, why is that? We can't get a probability greater than 1. It's not possible. Well, why is that the case? Well, it's because we've double counted. As you noticed here, I counted the 5 for the cats and I counted the 5 for the dogs, even though those are the same people twice, right? Because these people are being double counted as though they're two separate people, even though they're not, right? They're just people who own a cat and a dog, but it's still just, five unique people, right? So therefore, we have to subtract off the intersection of both. We have to subtract off this number, this 5 that's in here, in order to get the right answer. And if we do this, then we get the right answer, which, let's see, 15 plus 11. So we're going to get 21 over 21, which is 1, right? Which demonstrates that basically all the people in this example are either cat owners or dog owners, because I didn't put anyone out here on the side who wasn't either one of them. So, the probability that we'll get a cat owner or a dog owner is certain. We're certain to get one because the only people I put in this example were dogs or cat owners, right? But as you saw there, we got a probability greater than 1, which is impossible when we forgot to subtract off the people who are in common, right? And so it's very important that we make sure to do that. So let's do an example like this. It says, if a whole number between 1 and 10 is picked randomly, what is the probability the number is less than 5 or even? So these events are not mutually exclusive because there are some numbers that are less than 5 and even, right? 4 is less than 5 and it's even. 2 is less than 5 and it's even. So there's actually two intersections here, right? There's two times where we are going to get numbers, right? Certain outcomes that are going to be double counted, that are going to be counted in event A and in event B. And so we have to subtract them off so that we don't double count them, right? So that we subtract them off one time so that they're only counted that other time and not both times. So let's say event A is less than 5, and let's say event B, beautiful, love it, is an even number. Well, let's see. So probability of A is equal to what? Well, probability that the number is less than 5 would be 4 and 10, right? 4 over 10, because there's 4 numbers less than 5 that are between 1 and 10, 1, 2, 3, and 4. and then every other number is 5 or greater, so therefore 4 out of 10. And what's the probability of B, that the number is even? Well, half the numbers are even, right? 5 out of the 10 numbers are even. In this case, I'm actually not going to reduce the denominator. I'm not going to reduce to lowest terms because we're about to add these things up and subtract off the the intersection of these. And so we're only just going to have to change them to make them the same denominator again if we are to reduce them. So I'm actually just going to leave them in this form. I'm not reducing on purpose here, even though I realize I could. So now let's find out the probability of event A and B occurring. Let's think about that. Well, how many numbers are both even and less than 5? Well, there's two numbers. 2 is even and less than 5, and so is 4, right? So that's two numbers out of 10 that satisfy both these conditions, and so they were counted twice, right? 2 and 4 were counted here for event A and were counted a second time for event B, but they're really just the same two numbers, right? So given this, we know that probability of A union B would be equal to the probability of A plus the probability of B minus the probability of A and B together, right? Minus, the middle of our Venn diagram. That's going to equal 4 out of 10 plus 5 out of 10 minus 2 out of 10, which is equal to 7 out of 10. So in this case, actually, let's say we hadn't subtracted off the probability of A intersect B, we actually still would have got 9 out of 10. We still would have got something that's a feasible probability. However, it wouldn't have been the correct probability. It wouldn't have been very accurate, right? 7 out of 10 is more accurate. And to prove it, I'm actually going to write out all the numbers that satisfy both criteria. So 1, 2, 3, and 4 do, right? Because they're under 4. So they're one of those criteria. And then even numbers. So 6, 8, right? So these are the 6 numbers, and 10. These are the 7 numbers that satisfy this. The numbers that don't satisfy this are the 3 that are missing here, which are 5, 7, and 9. They don't satisfy this. So had we said 9 out of 10, that 9 out of the 10 numbers satisfied at least one of the conditions, that just wouldn't be true, right? If we're writing out these numbers and we're clearly seeing, oh wait, there's only 7 numbers that satisfy one or both conditions, because with the 9 out of 10 example, we actually double counted 2 and 4 and acted as though those were separate numbers from themselves again. So we'd add 2 and 4 to the list again, even though that isn't really, that's not really right? We already have 2 and 4. So that's why we had to subtract them off in order to be more accurate, right? 9 out of 10 would get part marks, but it would not be a fully accurate answer because we're forgetting a very key detail in this process. So do keep that in mind to remember to subtract off A intersect B. Now here's the thing with mutually exclusive events, there is nothing in A intersect B if the event is mutually exclusive, because there's no possible way to have event A and B occur at the same time in that case. And so that's why we're allowed to skip it, because if we didn't skip it, if we remembered it, it would just be minus 0, right? Because probability of A union B, A intersect B would be 0 in those cases. And so that's why we can just skip it, because subtracting 0 doesn't actually do anything for us, right? It doesn't actually matter. Good. Let's move on to example 3. So example 3 says, if a committee of 5 is to be chosen from 6 males and 8 females, what is the probability that the committee is all males or all females? Well, in this case, these events are mutually exclusive, right? If the event A is all males, then it's not possible to also at the same time have the committee be all females, and vice versa, right? If the committee is all females, then that means the committee is not all males. These are direct contradictions to one another, right? So let's write that down. Event A is all males, so an all male team. And event B is all females, so an all female team, right? All female team. Okay? So, what is the overall so now that we know these are mutually exclusive, what do we do next? We know the equation we'll be using is going to be this one. It's going to be that the probability of that one of these is the case, that we have A or B being the case, is equal to the probability of A plus the probability of B, right? The probability of A intersect B is nothing, right? It's not possible that we chose all males for our team and that we also chose all females for our team. These are in direct contradiction. So what do we need to find out? We need to find out the probability of A, and we need to find out probability of B separately, because when we add these together, we'll get the probability of A union B, which is the probability that either the team was all male or all female, so just all of any gender, right? As opposed to a specific one, all male or all female. Okay. All right, so probability of A is equal to what? Well, let's think about that. What is the total number of ways we could select a committee? Well, that's going to be 14 choose 5, right? Because with the committee, we don't care about the order that the people were chosen. If it's the same people chosen, regardless who is picked first, second, third, fourth, fifth, or sixth, or I guess just fifth because there's only 5 committee members, I'm just noticing here, then, it doesn't really matter the order they're chosen in because they're all either on the committee or they're not, right? They're all on the committee in this case. So, therefore, the denominator for both of these is going to be, let's see, is going to be 14 choose 5, right? There's 14 choose 5 ways to possibly form a committee with no restrictions. Now, for probability A, on top, we need to put on what are the number of ways within those 14 choose 5 total ways that we have an all male team. Well, there's 6 males, and we need to choose 5 of them, right? So that means that there are 6 ways, right? Right, there are 6 ways, right? If we plug this in our calculator, there are 6 different ways that we could choose an all male team over the 2002 ways we could choose any team. So it's very unlikely if we randomly choose that it's going to be an all male team. And the same is true to some degree for an all female team, right? Because an all female team would mean that we would need to do 8 choose 5. So we have 8 females, we're going to choose any 5 of them. Now there's a few more ways to do this than there are for the all male team because there are more females, and so there's more different combinations of females that we could choose to be on an all female team, but this still doesn't account for very many of the 2002 possibilities. The vast majority of the teams possible are teams that include both genders, right? That include both males and females, right? Okay, so let's do probability A, 6 over 2002, plus probability B, 56 over 2002, which is going to be 62 over 2002, which is about 0.03 or 3%. So it is very unlikely that it'll be an all male or an all female team. It's a lot more likely, understandably, that there's going to be both males and females on the team, or at least one male and one female on this team is a lot more likely than having the team be either all male or all female. Very good. So this is a good question. Okay, this is a good test question, I must say. I'm not saying it to be on the test, but I'm saying this would make a good test question to possibly be there because it tests a lot of different things. It tests, we have to understand that it's mutually exclusive. We have to figure out that, and then, therefore apply the equation to it. And then we also need to revisit basic probabilities and also revisit combinations and recognize that these are combinations, not permutations. So there's quite a few different elements to this one in order to make it work, right? In order to really understand this. Okay, let's do one last question, and then I promise we will be done with this unit, or at least this unit's lectures, after I do one more example here. But it's an important one, so let's not skip it. It says, in a recent grade 12 survey, it is estimated that 20% of the students are over 18 and 50% of the students can drive. If 10% of the class is over 18 and can drive, what is the probability that someone from the class is either over 18 or they can drive? So let's write out our events and let's first decide if the events are mutually exclusive or not. So event A is that somebody is over 18 years old. And event B is that the person can drive. Are these mutually exclusive or not? These are not mutually exclusive because it is possible that the same person is over 18 and can drive. Now, maybe this would be mutually exclusive if the age was like, under 10, right? Because no one under 10 is able to drive, right? You're either under 10 or you can drive, or maybe neither of them, but both can't occur. But there's lots of people who are over 18 and who can drive. And so these are not mutually exclusive because it is certainly possible. In fact, most people who can drive are over 18, and also most people over 18, and at least in Canada, probably, probably can drive, right? Okay, so the fact that they're not mutually exclusive means what? That means we must use the non mutually exclusive equation, which says that A or B, right? We want to figure out the probability that either A is true or B is true, right? The probability that either someone from the class is over 18 or they can drive, or both potentially, right? And that's going to be equal to probability of A plus the probability of B minus the probability of A and B being true, right? Not because we want to take away that possibility, but because we don't want to count it twice. So we're taking away it just once so that it only actually occurs once in our data set. Good. Okay, so what's the probability of A? What's the probability that someone is over 18 years old? It says 20%. It was estimated that 20% of the students are over 18. So that means the probability is 0.2 if we put that into decimal form. What is the probability of event B, of the probability that a randomly selected grade 12 person can drive? Well, 50%, 0.5 would be our probability that somebody can drive. Then it says if 10% of the class is over 18 and can drive, so basically 10% of the people are people in both categories who are being double counted if we just add them and do nothing else, then what is the probability that someone from the class is either 18 or they can drive? Well, now all we need to do is plug these equations, or we need to plug our findings in and say this is equal to 0.2 plus 0.5 minus 0.1, which is 0.7 minus 0.1, which is 0.6, right? So therefore, the probability that someone from the class is either 18 or they can drive is 0.6. So slightly likely chance that someone randomly selected is in at least one of these categories. Maybe both, or maybe just one of the categories. Very good. All right. Well, you know what? Congratulations. That is not only it for today's class, that is it for the unit. Next unit, we're going to be talking about probability distribution. So there's quite a few more things about probability we haven't done yet. Probability is a huge topic, so we will continue that in Unit 4. Good work, everyone, and I'll see you for Unit 4. Bye, everyone.